Hi everyone. Today we're going to talk about the Decay series. A Decay series is just a visual representation. You might say it's a graph that represents what happens to a particular isotope over time as it decays. Many of the isotopes that we are familiar with actually don't stop by just emitting an alpha particle or a beta particle or something like that. They actually go through a series of different steps. And so this particular decay series right here, we've got at the top in the upper right hand corner, we have uranium-238. So I'll circle that right there. Uranium-238. And the other thing you're going to want to notice is that on the left side here on the y-axis, we've got the mass number. Remember, mass number is protons plus neutrons. On the x-axis, we've got atomic number. That's the number of protons. So this would be uranium, element number 92 or 92 protons. And it's got a mass number of 238. So uranium-238. It decays initially via, and it might be hard to see, this is really small right here, but I'll try to circle it, by an alpha emission. And when it does that, it becomes thorium-234. And thorium-234 is unstable. And so thorium-234, I'm going to erase that little bit that I just did there because you can't see what I'm about to point out. It decays via beta emission, beta negative emission, and so on and so forth. So it keeps going. So then it becomes protactinium-234 and then uranium-234 again. So it goes back to being uranium and it keeps going, keeps going, keeps going. Eventually, where does it stop decaying? Well, you can see at the very bottom here, and it's actually in a different color on this particular one, not on every decay series, but it ends up becoming lead-206, which is stable, and so it's no longer going to give off any sort of radiation because it doesn't need to. So that's basically how you read a decay series. You need to just, orient yourself when you first look at it and see, like on this particular one, a blue line represents an alpha decay, and you can see the little tiny alpha. And the red line indicates a beta decay. The thing that's interesting on this particular decay series for uranium-238 is that in the middle of the decay, we eventually have an element or an isotope that's of interest. This is radon-222, and radon-222 is really an interesting element because it's a gas. Now, most of these are solids at room temperature, but radon is a gas at room temperature. Radon is an alpha emitter, and you've learned from your penetrating power lab that alpha emitters are not particularly dangerous, not something we have to worry about safety-wise. However, if you inhale them or if you ingest them, swallow them, they can be problematic. And of course, since radon-222 is a gas, if you breathe it in, and especially if you breathe it in on a regular basis, it raises your risk significantly for lung cancer. So radon is actually, and this may change with time, but currently the leading cause of lung cancer is smoking. Of course, smoking rates have gone down pretty significantly in the past, maybe 20 years, I'd say, maybe 30 years. But radon is still being emitted. Radon is especially problematic in areas where there is a lot of granite bedrock. So that's underneath your house, underneath, the dirt. And granite often has some uranium in it. And uranium, if it's decaying, if it's uranium-238 and decaying, eventually you might end up with radon-222. If there's a crack in the foundation of your home, if you have a basement, it can kind of leak up into your house. Luckily for us in Orange County, there isn't a ton of bedrock, granite bedrock. But there are patches of it, and I actually have a friend who bought a house up in Hillsborough, and she had radon in the basement. Luckily, you can mitigate that if you know that it's there, and there are systems that they can put in place to basically fans and things to pump the air out, and so it'll make it less concentrated. But generally speaking, in this area, it's not a huge issue. So we already have talked about this a little bit, but why do atoms emit radiation? Remember, we said it's because they're unstable. So one of those three types of radiation we talked about, alpha, beta, or gamma, is going to be emitted if an atom's nucleus is unstable. The way you can determine if an atom is going to be unstable is by looking at the ratio of neutrons to protons. This graph to the right here, this is a graph of something called the band of stability. Generally speaking, you will see in textbooks and various resources that generally atoms with a number of neutrons that's equal to or slightly greater than the number of protons tend to be stable. And that statement needs to be explained a little bit, because equal to, that would be, for example, when the atom is quite small. So if you look again, here's a graph. This has got protons on the x-axis. This time it has neutrons on the y-axis. So you notice this straight line right here, this is not a line showing any sort of isotope. It's simply a reference line. This line shows us what the line for a 1-to-1 ratio for protons to neutrons would be. But this right here, it almost forms kind of a line. That's called the band of stability. And you may, if you look carefully, you'll notice that there are little dots there. And each dot represents an isotope that is actually stable. And so you'll notice when the atom, or when the nucleus is fairly small, like maybe 10 protons or smaller, so that would be the element neon, or anything smaller than that. Generally, about a 1-to-1 ratio is what you see for stability of protons to neutrons. If you get, more neutrons than that, then you're going to end up with an unstable atom or unstable nucleus. So like if we graphed it and we had, a lot more neutrons compared to our protons, then that would make it really unstable. Same thing, the opposite direction would make it really unstable. But as the nucleus gets bigger and bigger, as we get bigger nuclei, you notice that you need even more neutrons to keep the nucleus stable. And so, it's equal really early on, numbers of protons and neutrons, but as it gets much bigger, then you've got to have way more neutrons to keep it stable. So like I just mentioned, this area right here, this is called the band of stability. So all of these are isotopes that are actually stable. Generally speaking, a 1-to-1 ratio early on when it's a small nucleus, but as it becomes a bigger and bigger nucleus, you need more and more neutrons. And sometimes you'll hear people say that neutrons are the glue that holds the nucleus together. Are they literally the glue? Of course not. But having neutrons to kind of mitigate the positive charge of the protons, causing them to repel each other, is going to be important for stability. This graph right here is just, I think, a really pretty graph that does a nice job of showing the band of stability. The black right here, see where it says black is stable nuclide. Nuclide is basically another way of saying a stable nucleus. So all the black dots right here are representing stable. So that's the band of stability in this case. Remember, this straight line right here is just a reference. It gives us a 1-to-1 ratio, what that would look like. And then the thing that's cool about this graph is if you're on this side, like in the blue, that means you have a lot more neutrons, right? Well, if you have more neutrons than protons, then you're probably going to have beta negative emission. If you have fewer protons than neutrons, then you're going to have beta positive emission. You can see the alpha, the yellow, So remember, alpha are big compared to compared to beta positive and beta negative. When you have really big stuff, big disproportion there between the protons and the neutrons, then you start giving off big particles like alpha particles. There's some other things in here that we haven't talked about. Fission we'll get into when we get into nuclear power. And protons and neutrons we haven't really talked about, but I still think this is quite a nice graph.